Imagine looking up at the night sky and knowing that somewhere out there, racing through the darkness at 60 kilometers per second, is something that shouldn't exist. Something so massive, so ancient, and so utterly alien that it's forcing scientists to question everything they thought they knew about our cosmic neighborhood. Well, that something has a name, and it's currently hurtling toward the inner solar system right now. Hello there, and welcome to the Sleepy Astronaut, where tonight we're diving into one of the most perplexing astronomical discoveries of our time. I'm here to guide you through the strange and captivating story of 3I Atlas, an interstellar visitor that's got astronomers scratching their heads and asking questions they never thought they'd need to ask. Before we venture into this cosmic mystery together, I'd love to know where in the world you're watching from and what draws you to the wonders of space. Are you a seasoned stargazer or someone who simply finds comfort in pondering the infinite? Either way, you're in exactly the right place because what we're about to explore might just change how you think about our place in the universe. If you find yourself captivated by these cosmic tales, I'd be incredibly grateful if you could give this video a thumbs up and perhaps consider subscribing. It helps more curious minds like yourself discover these stories, and honestly, the universe is far too fascinating to explore alone. Now, let me paint you a picture of what we're dealing with here. On July 1st, 2025, the Atlas telescope system in Chile detected something extraordinary. At first glance, it looked like just another space rock, but as astronomers began studying its trajectory, they realized they were looking at something that had traveled unimaginable distances to reach us. This wasn't just any asteroid or comet. This was a visitor from another star system entirely. 3I Atlas earned its designation as the third confirmed interstellar object ever discovered, joining the mysterious Oumuamua and the more conventional comet Borisov in this exclusive club of cosmic wanderers. But here's where things get interesting, and I mean really interesting. This object is unlike anything we've seen before, and new images from some of our most powerful telescopes are revealing details that have scientists both excited and deeply puzzled. What makes 3I Atlas so remarkable isn't just its origin, it's its sheer size. We're talking about an object roughly 7 miles wide, making it absolutely massive compared to its interstellar predecessors. To put that in perspective, the famous Oumuamua was only about the size of a football field, while 3I Atlas could swallow entire cities. It's the largest interstellar object we've ever had the privilege to study, and that alone makes it scientifically invaluable. But size is just the beginning of this story. The more astronomers observe 3I Atlas, the more questions arise. Its trajectory through our solar system follows a hyperbolic path with an eccentricity of 6.2, meaning it's moving faster and on a straighter course than any interstellar visitor we've encountered. While previous objects approached our Sun head-on relative to our star's motion through the galaxy, 3I Atlas is coming at us sideways, perpendicular to the Sun's path. It's as if the universe decided to throw us a cosmic curveball. Perhaps most intriguingly, this ancient wanderer might be older than our entire solar system. Think about that for a moment. While our sun and planets were still forming from cosmic dust and gas, 4.6 billion years ago, 3I Atlas may have already been drifting through the void between stars. Some estimates suggest it could be anywhere from 7 to 11 billion years old, making it potentially the oldest comet humanity has ever laid eyes upon. This age raises profound questions about what 3I Atlas might tell us about the early universe. If it truly predates our solar system, then the water, ice and organic materials locked within its nucleus could represent some of the most pristine cosmic ingredients ever preserved. We're essentially looking at a time capsule from an era when the galaxy was young and star formation was far more chaotic than it is today. The Vera C. Rubin Observatory, with its revolutionary precision and sensitivity, managed to capture detailed images of 3I Atlas, even before its official discovery. These photographs, taken between June 21st and July 7th, 2025, revealed the object's impressive scale and provided our first clear look at this interstellar giant. The fact that such a sophisticated instrument detected 3I Atlas before any other telescope speaks to both the observatory's capabilities and the object's significance. But here's where our story takes an unexpected turn. When scientists began analysing the spectroscopic data from 3I Atlas, they discovered something puzzling. Unlike typical comets, which show clear signatures of gas sublimating from their surfaces as they approach the Sun, 3I Atlas displays unusual characteristics that don't fit the standard comet playbook. Initial observations revealed that its coma, the cloud of material surrounding the nucleus, contains water ice and silicate grains. So far, so normal for a comet. However, deeper analysis showed that the spectrum lacks the expected fingerprints of atomic or molecular gas that should be streaming away from an active comet. Instead, astronomers are seeing evidence of dust and what appears to be reddening of reflected sunlight, suggesting surface properties unlike anything in our cosmic backyard. Even more perplexing is the object's lack of periodic brightness variations. Most comets tumble as they travel, causing their brightness to fluctuate in predictable patterns as different surfaces reflect sunlight toward Earth. But 3I Atlas maintains remarkably steady brightness, as if it's not rotating in the chaotic manner we'd expect from a natural object. This stability has raised eyebrows throughout the astronomical community. The mystery deepens when we consider 3I Atlas's remarkable activity levels. Even when it was over 6 astronomical units from the Sun, roughly the distance of Jupiter, it remained bright and active. This suggests that whatever's driving its coma formation isn't just water ice sublimating in the solar wind, but potentially more exotic volatile compounds that remain active at much greater distances and lower temperatures. As 3I Atlas continues its journey toward its closest approach to the Sun on October 30th, 2025, astronomers around the world are training their most powerful instruments on this enigmatic visitor. The James Webb Space Telescope has already scheduled observation windows in August and December, before and after the object's closest solar approach. These infrared observations should reveal the composition of 3I Atlas in unprecedented detail, potentially detecting water vapor, carbon monoxide, carbon dioxide, and ammonia in its coma tail. But perhaps the most intriguing aspect of this story isn't just what 3I Atlas is, but what its discovery might mean for our understanding of interstellar space. For decades, astronomers theorized about objects drifting between the stars, but actually finding them proved nearly impossible. Now, with improved detection capabilities and surveys like Atlas continuously monitoring the sky, we're entering an era where interstellar visitors might become regular discoveries rather than once-in-a-lifetime events. The Rubin Observatory alone is expected to discover millions of new asteroids and potentially dozens of interstellar objects within its first few years of operation. This technological revolution means that 3I Atlas might not be an anomaly, but rather the first of many such discoveries that will fundamentally change our understanding of how material moves between star systems. What makes these interstellar visitors so scientifically valuable is their completely foreign nature. Every planet, moon, asteroid, and grain of dust in our solar system shares a common origin story. They all formed from the same disk of material that surrounded our young sun billions of years ago. But objects like 3I Atlas are true outsiders, formed in completely different stellar environments under conditions we can only imagine. By studying the composition, structure, and behavior of these cosmic refugees, we gain unprecedented insights into how other planetary systems form and evolve. Are the building blocks of planets similar throughout the galaxy? Or does each star system develop its own unique chemical signature? Do comets from other systems behave like ours, or do they follow entirely different physical laws based on their formation conditions? These questions become even more compelling when we consider the sheer diversity we've already observed among interstellar objects. The mysterious Oumuamua displayed characteristics unlike any comet or asteroid we'd seen, accelerating away from the Sun without any visible outgassing and maintaining an extreme cigar-like shape. Comet Borisov, on the other hand, behaved much more like comets from our own solar system, complete with a beautiful tail of gas and dust. Now, 3I Atlas presents us with yet another puzzle, displaying some comet-like properties while defying others. It's active like Borisov, showing clear evidence of material streaming away from its nucleus, but its spectrum and rotation patterns suggest something more complex is happening beneath the surface. The timing of 3I Atlas's arrival is particularly fortuitous for astronomical research. Unlike Oumuamua, which was discovered only after it had already passed its closest approach to the Sun and was racing away from us, 3I Atlas was spotted early in its journey through the inner solar system. This advance warning gives astronomers months to plan observations, coordinate international research efforts, and potentially even consider spacecraft missions to study the object up close. Speaking of spacecraft missions, some researchers have already begun exploring the possibility of redirecting existing space probes to intercept 3I Atlas. The Juno spacecraft, currently orbiting Jupiter, could theoretically be maneuvered to encounter the interstellar visitor in March 2026 using a Jupiter gravity assist. Such a mission would provide unprecedented close-up data about an interstellar object, potentially answering questions that ground-based telescopes simply cannot address. However, the engineering challenges and costs associated with such a mission are substantial, and space agencies would need to weigh the scientific benefits against other planned missions and budget constraints. Still, the mere fact that such encounters are being seriously discussed highlights the extraordinary scientific value that 3I Atlas represents. As we continue to monitor this ancient wanderer's passage through our solar system, each new observation adds another piece to an increasingly complex puzzle. The water ice detected in its coma might represent some of the oldest and most pristine H2O molecules ever observed, formed in a planetary system that existed when our own was nothing more than a disk of cosmic dust. The organic compounds and silicate grains streaming away from 3I Atlas could provide direct samples of materials from another star's family of worlds, offering us an unprecedented opportunity to compare the chemistry of different stellar environments. In essence, this 7-mile-wide time capsule is delivering samples from across the galaxy directly to our cosmic doorstep. But there's something else about 3I Atlas that's captured the attention of researchers worldwide, something that pushes the boundaries of conventional astronomical thinking and ventures into territory that makes even seasoned scientists pause and reconsider their assumptions about what might be possible in the vast darkness between stars. This brings us to what might be the most controversial aspect of the entire 3I Atlas story. And it's something that's been quietly circulating through academic circles while generating heated debates in research institutions around the world. You see, when astronomers began plotting the object's trajectory with unprecedented precision, they discovered something that defied statistical probability in ways that made even the most skeptical researchers take notice. 3I Atlas approaches Venus, Mars, and Jupiter with a probability of less than 0.005%. To put that in perspective, imagine throwing a dart at a world map while blindfolded and hitting a specific building in a specific city. That's roughly the likelihood we're talking about here. For a random object drifting through interstellar space to just happen to pass so close to multiple planets in our solar system stretches the boundaries of coincidence to their breaking point. But the statistical anomalies don't stop there. The object's orbital plane sits at a low retrograde tilt to the ecliptic, the imaginary plane where most planets orbit our Sun. This particular orientation offers what researchers describe as various strategic advantages for any intelligence that might want to survey our solar system while remaining relatively undetected. It's the kind of trajectory that would allow prolonged observation of our planetary neighborhood with minimal risk of detection or interference. Now, before you start picturing little green beings piloting a 7-mile-wide spacecraft through our cosmic backyard, let me be clear about something. The overwhelming majority of astronomers studying 3I Atlas believe it's a natural object, a comet that's simply exhibiting unusual but ultimately explainable characteristics. The scientific consensus remains firmly rooted in conventional explanations, and there are perfectly reasonable ways to account for most of what we're observing. However, the fact that these questions are being raised at all speaks to just how extraordinary this object truly is. When an interstellar visitor displays enough anomalous properties to prompt serious researchers to explore unconventional hypotheses, we're clearly dealing with something that challenges our understanding of what's normal in the cosmos. The debate has been particularly intense because of how 3I Atlas compares to our previous interstellar visitors. Oumuamua famously exhibited non-gravitational acceleration, speeding up as it moved away from the Sun without any visible signs of outgassing that would typically explain such behaviour. This led to speculation about everything from exotic ice compositions to, yes, artificial origins. Comet Borisov, by contrast, behaved exactly as we'd expect a natural comet to behave, complete with predictable outgassing patterns and orbital mechanics. 3I Atlas falls somewhere between these extremes. It shows clear signs of cometary activity, with water ice and dust streaming away from its nucleus, but it also displays that puzzling lack of rotational variation and those statistically improbable orbital characteristics. It's as if the universe decided to give us a cosmic Rorschach test, presenting us with an object ambiguous enough to trigger our deepest curiosities and wildest theories. The timing of these observations couldn't be more significant. We're living through a golden age of astronomical discovery, with new instruments and detection methods revealing phenomena that previous generations of scientists could only dream about. The Transiting Exoplanet Survey satellite has shown us that 3I Atlas remained active even at distances of over 6 astronomical units from the Sun, far beyond where normal water ice should sublimate. The James Webb Space Telescope will soon provide infrared spectroscopy that could detect molecular signatures invisible to ground-based observations. Each new piece of data adds complexity to an already intricate puzzle. The object's composition appears to match a combination of Tagish Lake meteorite material and water ice, suggesting a mixture of organics, silicates, carbonate minerals, and significant amounts of frozen water. This composition isn't unusual in itself, but the way these materials are distributed and behaving as 3I Atlas travels through our solar system continues to surprise researchers. What's particularly fascinating is how 3I Atlas challenges our assumptions about the density and distribution of interstellar objects. For decades, astronomers estimated that such visitors should be extremely rare, perhaps one every few years if we were lucky. But the rapid succession of discoveries, Oumuamua in 2017, Borisov in 2019, and now 3I Atlas in 2025, suggests that interstellar space might be far more populated than we previously imagined. This has profound implications for our understanding of planetary formation and stellar evolution throughout the galaxy. If large objects like 3I Atlas are regularly ejected from other star systems during their chaotic early years, then the space between stars might be filled with a hidden population of wandering worlds, rogue planets, and massive comets that we're only just beginning to detect. The technological advances that made 3I Atlas's discovery possible also hint at what the future might hold. The Vera C. Rubin Observatory, which captured those crucial early images, will begin its legacy survey of space and time in the coming years, scanning the entire visible sky every few nights. This comprehensive monitoring system is expected to discover millions of new asteroids and potentially dozens of interstellar objects within its first operational period. Imagine living in a world where interstellar visitors become routine discoveries rather than once-in-a-generation events. Each new object would carry with it samples from distant star systems, organic compounds forged in alien environments, and ice that condensed in the cold depths between stars billions of years ago. We'd essentially have a cosmic delivery service bringing us materials from across the galaxy, each package telling us something new about how planets form and evolve in different stellar neighborhoods. But there's something uniquely special about 3i Atlas that sets it apart from what we might expect from future discoveries. Its enormous size makes it visible to ground-based telescopes for months, giving researchers unprecedented opportunities to study an interstellar object in detail. Most of the objects we're likely to discover in the future will be much smaller, visible for only brief periods before disappearing back into the cosmic darkness. This extended observation window has allowed astronomers to notice subtle details that might have been missed with a more fleeting visitor. The object's steady brightness, its unusual spectroscopic signature, and those statistically improbable orbital characteristics all became apparent only through careful, repeated observations over weeks and months. A smaller, faster-moving object might have passed through our solar system without revealing these intriguing anomalies. The story of 3i Atlas also highlights how much our detection capabilities have improved in just the past few years. The Atlas survey system that discovered the object represents a new generation of automated sky monitoring programs designed to spot potentially hazardous asteroids. These systems scan the heavens continuously, comparing each night's observations with previous images to identify anything that's moved or changed. It's almost poetic that a system designed to protect Earth from cosmic impacts ended up discovering something that might fundamentally change our understanding of our place in the galaxy. The same technology that watches for dangerous asteroids has opened a window into the population of objects drifting between stars, each one a messenger from distant worlds we may never visit, but can now study in ways our ancestors could never have imagined. The international collaboration that's emerged around 3i Atlas observations also demonstrates how modern astronomy operates as a truly global enterprise. Ground-based telescopes in Chile capture initial discovery images. Space-based observatories like TESS monitor the object's activity levels, and the James Webb Space Telescope provides detailed spectroscopic analysis. Each instrument contributes a piece of the puzzle, building a comprehensive picture that no single observatory could achieve alone. This collaborative approach becomes even more important when studying interstellar objects because of their limited visibility windows. Unlike asteroids or comets from our own solar system, which can be observed repeatedly over many orbital periods, interstellar visitors offer only one chance for detailed study. Once 3i Atlas completes its passage around the Sun and heads back into interstellar space, it will be gone forever, taking its secrets with it unless we've managed to unlock them during this brief cosmic encounter. The pressure to maximize every observation opportunity has led to some of the most intensive astronomical campaigns in recent history. Research teams around the world have coordinated their efforts to ensure that 3i Atlas is being monitored continuously across multiple wavelengths of light. Radio telescopes listen for any unusual emissions, optical instruments track its brightness and color changes, and infrared observatories probe the composition of materials streaming away from its nucleus. Even as 3i Atlas continues its journey toward its October close approach to the Sun, new mysteries continue to emerge. Recent observations have detected what appears to be structural complexity within the object's coma, suggesting that multiple sources of outgassing might be active across its surface. This kind of heterogeneous activity could explain some of the unusual spectroscopic signatures that have puzzled researchers since the object's discovery. The question of what happens next in the 3i Atlas story remains tantalizingly open. Will the James Webb Space Telescope's infrared observations reveal exotic compounds that definitively mark the object as originating from a chemically distinct stellar environment? Might ground-based telescopes detect periodic variations in brightness that finally reveal the object's rotation period and a shape? Or could we discover something even more unexpected, something that pushes the boundaries of our understanding even further into uncharted territory? As we approach 3i Atlas's closest encounter with our Sun, scheduled for October 30th, the astronomical community finds itself holding its collective breath. You see, this isn't just another routine observation campaign. What we're witnessing might represent a fundamental shift in how we understand the very nature of objects that drift through the cosmic void between stars. The timing couldn't be more perfect for unraveling these mysteries. Unlike its predecessors, which either arrived unannounced or departed before we could properly study them, 3I Atlas has given us the gift of time. Months of advance warning, months of careful observation, and crucially, months to notice patterns that might have otherwise slipped by undetected. And those patterns are becoming increasingly difficult to ignore. The object's behaviour as it approaches the inner solar system has defied several key predictions that astronomers made based on our understanding of cometary physics. Most comets become more active as they near the Sun, their surfaces heating up and releasing ever greater quantities of gas and dust. But 3I Atlas seems to march to the beat of its own cosmic drummer. Temperature measurements suggest that the object's surface should be warm enough to trigger significant water-ice sublimation, yet the spectroscopic signatures remain stubbornly consistent with what we observed when it was much farther away. It's as if 3I Atlas has found a way to regulate its own activity levels, maintaining a steady output regardless of how much solar energy it receives. This kind of thermal regulation is virtually unknown among natural comets. Ice subliments when it reaches certain temperatures, period. There's no negotiating with physics, no cosmic thermostat that allows a chunk of frozen material to decide how much gas to release. Yet here we have an object that seems to be doing exactly that, maintaining consistent activity levels across a range of solar distances where we'd expect dramatic changes. The implications of this behaviour extend far beyond simple curiosity about one unusual object. If 3I Atlas truly represents a new class of interstellar body, one with properties we've never encountered before, then our models for how planetary systems form and evolve might need fundamental revision. The building blocks of worlds might be far more diverse than we ever imagined. Consider what this means for our understanding of planetary formation in other star systems. We've always assumed that the basic physics of ice, rock, and gas operates the same way throughout the galaxy. Water freezes at the same temperature, silicate minerals form the same crystal structures, and gravity pulls objects together following the same mathematical laws. But what if there are processes we've never encountered, chemical compositions we've never seen, or physical phenomena that only emerge under conditions that don't exist in our solar system? 3I Atlas might be our first glimpse into a universe far stranger and more varied than we've dared to imagine. The object's ancient age suggests it formed during an era when the galaxy was younger, more chaotic, and possibly governed by different rules than what we observe today. Star formation rates were higher, stellar collisions more common, and the heavy elements that make rocky planets possible were distributed in patterns unlike anything we see in our current cosmic neighbourhood. The water ice locked within 3I Atlas's nucleus could represent some of the oldest frozen molecules in existence, condensed from gas clouds that surrounded stars when the universe was a fraction of its current age. These pristine materials have been preserved in the deep freeze of interstellar space for billions of years, maintaining their original chemical signatures like a cosmic time capsule waiting to be opened. But here's where the story takes another unexpected turn. Recent analysis of the object's trajectory has revealed something that's causing quiet discussions in astronomical circles worldwide. When researchers traced 3I Atlas's path backward through time, accounting for the gravitational influences of nearby stars and the galaxy's overall rotation, they discovered that the object's origin point doesn't match any known stellar neighbourhood. Most interstellar objects should be traceable back to specific star systems, or at least general regions of the galaxy, where they could have been ejected during planetary formation. But 3I Atlas appears to have emerged from what astronomers are calling a stellar desert, a region of space with unusually low star density that shouldn't have been capable of producing such a massive object. This geographical mystery adds another layer of complexity to an already puzzling visitor. Either our understanding of stellar evolution and planetary formation is incomplete, or 3I Atlas has travelled much farther and for much longer than its trajectory suggests. The possibility that it's a true intergalactic wanderer an object that escaped not just its birth star system, but our entire galaxy, remains tantalizingly open. The technical challenges of studying such an ancient, distant object have pushed observational astronomy to its absolute limits. Ground-based telescopes are operating at the edge of their sensitivity, capturing photons that have travelled unimaginable distances to reach Earth. Each spectrum, each brightness measurement, each tiny variation in colour represents information that's taken billions of years to arrive at our instruments. Space-based observatories offer even more remarkable capabilities. The James Webb Space Telescope's infrared vision can peer through the dust and gas surrounding 3I Atlas to analyse the composition of materials that haven't been exposed to stellar radiation since the object's formation. These observations might reveal molecular signatures that exist nowhere else in our solar system, organic compounds forged in stellar environments we can barely comprehend. The Transiting Exoplanet Survey satellite has provided a continuous monitoring capability that ground-based telescopes simply cannot match. Its unblinking electronic eyes have tracked 3I Atlas through day and night cycles, weather patterns, and atmospheric disturbances that would interrupt Earth-based observations. This constant vigilance has revealed subtle variations in the object's behaviour that might have been missed by more intermittent observation campaigns. Even amateur astronomers have contributed to the 3I Atlas research effort, their backyard telescopes adding data points to a global network of observers. The democratization of astronomical observation means that discoveries like this engage not just professional researchers, but citizen scientists around the world, each contributing their own small piece to humanity's understanding of this cosmic visitor. The cultural impact of 3I Atlas extends far beyond the scientific community. Social media platforms buzz with speculation about the object's nature, artists create visualizations of its journey through space, and writers craft stories about what it might mean for humanity's place in the cosmos. This kind of public engagement with astronomical discovery represents something new in human history. A global conversation about our cosmic neighbourhood that includes voices from every corner of our planet. Educational institutions have seized upon 3I Atlas as a teaching opportunity, using its story to introduce students to concepts ranging from orbital mechanics to spectroscopy to the deep history of the galaxy. Children who learn about this ancient wanderer today might grow up to become the scientists who discover the next generation of interstellar visitors, armed with instruments and techniques we can barely imagine. The economic implications of interstellar object research are also beginning to emerge. The technologies developed to study 3I Atlas, from advanced imaging sensors to sophisticated data analysis algorithms, often find applications in fields ranging from medical imaging to materials science. The investment in astronomical research pays dividends in unexpected ways, driving innovation that benefits society far beyond the realm of pure science. Private space companies have begun expressing interest in interstellar object research, recognizing that the technical challenges of studying these cosmic visitors could drive advances in spacecraft design, navigation systems, and long-duration mission planning. The prospect of eventually sending robotic probes to intercept future interstellar objects represents a new frontier for commercial space exploration. International cooperation around 3I Atlas observations has also demonstrated how scientific collaboration can transcend political boundaries and cultural differences. Research teams from nations that rarely agree on anything else have shared data, coordinated observations, and jointly published findings about this shared cosmic heritage. In a world often divided by conflict and competition, the study of interstellar visitors offers a reminder of our common humanity and shared curiosity about the universe. The philosophical implications of 3I Atlas's visit stretch even deeper than its scientific significance. Here we have an object that predates our entire solar system, a wanderer that has drifted through the galaxy since before Earth existed. Its journey through space encompasses timescales that dwarf human history, carrying within its frozen nucleus a record of cosmic events that occurred when the universe was fundamentally different from what we know today. The humbling nature of this perspective cannot be overstated. We live our lives on a small, rocky planet, orbiting an ordinary star in an unremarkable corner of a typical galaxy. Yet occasionally, the cosmos delivers to our doorstep artifacts from its deep history, objects that connect us to the broader story of matter and energy, unfolding across billions of years and countless star systems. Star. 3i Atlas reminds us that we are part of something vast and ancient, a cosmic web of material and energy that has been evolving since the universe began. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these elements were forged in the nuclear furnaces of distant stars and scattered into space when those stars reached the end of their lives. In a very real sense, we are made of stardust, and objects like 3i Atlas help us trace our cosmic ancestry back to its origins. The religious and spiritual dimensions of such discoveries also deserve recognition. Different faith traditions interpret astronomical findings in various ways, but many find in objects like 3i Atlas a confirmation of the universe's grandeur and mystery. The idea that ancient materials from distant star systems can visit our cosmic neighborhood speaks to concepts of cosmic unity and interconnectedness that resonate across many belief systems. As 3i Atlas continues its approach toward the Sun, researchers are preparing for what might be the most intensive observation campaign in astronomical history. Every major observatory on and off Earth will focus its attention on this ancient visitor during its closest solar approach. Radio telescopes will listen for any unusual emissions, optical instruments will track every change in brightness and color, and infrared observatories will analyze the composition of materials streaming away from its surface. The coordination required for such a campaign rivals that of major military operations. Observation schedules must be synchronized across multiple time zones, data formats standardized between different instruments, and research teams prepared to respond quickly to unexpected discoveries. The window of opportunity is limited, and the stakes couldn't be higher. Weather patterns at ground-based observatories become matters of international concern. A storm system that clouds the skies over a major telescope during a crucial observation window could mean the loss of irreplaceable data. Backup plans and alternative observation sites are prepared, but the finite nature of 3i Atlas's visit means that some opportunities once missed will never return. The pressure on individual researchers participating in these campaigns is intense. Years of career development and scientific reputation can hinge on the quality of data collected during a few critical nights of observation. Graduate students find themselves responsible for operating million-dollar instruments, while senior scientists coordinate international teams of colleagues they may have never met in person. Yet despite the pressure and complexity, there's also an undeniable excitement that permeates the astronomical community. This is why many researchers chose careers in astronomy in the first place, the opportunity to study something genuinely new and potentially revolutionary. The chance to be among the first humans to understand what 3i Atlas truly represents drives researchers to work longer hours, accept greater risks, and push their instruments to absolute performance limits. The data flowing in from these intensive observations is already revealing new details about 3i Atlas's structure and composition. High-resolution imaging suggests that the object may not be a single, solid body, but rather a collection of smaller components held together by weak gravitational forces. This kind of rubble pile structure is common among asteroids in our solar system, but its presence in an interstellar object raises questions about how such loose assemblages could survive the gravitational stresses of ejection from their parent star system. Spectroscopic analysis continues to reveal unexpected chemical signatures. Trace amounts of complex organic molecules have been detected in the object's coma, compounds that shouldn't exist in the harsh radiation environment of interstellar space. These molecular fossils suggest that 3i Atlas's journey between stars may have been shorter than originally estimated, or that it has been protected by some mechanism we don't yet understand. The mystery deepens with each new observation, and as we approach the climactic moment of 3i Atlas's closest solar encounter, the astronomical community finds itself balanced on the edge of discovery. What we learn in the coming weeks might reshape our understanding of planetary formation, stellar evolution, and the distribution of materials throughout the galaxy. But perhaps most importantly, 3I Atlas has reminded us that the universe still holds surprises. In an age when we sometimes feel that science has answered all the big questions, this ancient wanderer has arrived to show us just how much we still don't know. It's a humbling reminder that curiosity remains our most valuable tool for understanding the cosmos, and that the next great discovery might be hurtling toward us through the darkness, right now, waiting to challenge everything we thought we knew about our place in the vast expanse of space and time. The anticipation surrounding 3I Atlas's October approach has created something of a perfect storm in the astronomical community. Every major research institution is vying for observation time, and the competition for telescope access has become more intense than anyone anticipated. It's rather like watching the entire scientific world hold its breath at once, waiting to see what secrets this ancient traveller might reveal when it finally reaches its closest point to our Sun. What makes this moment particularly fascinating is how the object's behaviour continues to confound expectations even as we get better data. You'd think that more observations would lead to clearer answers, but 3I Atlas seems determined to keep us guessing. Each new spectrum brings fresh puzzles, each brightness measurement reveals unexpected variations, and the more we learn about this cosmic visitor, the more questions seem to multiply. The latest infrared observations have detected something particularly intriguing within the object's coma. Researchers are finding evidence of crystalline water ice, which shouldn't exist in an object that's spent billions of years in the cold depths of interstellar space. Crystalline ice forms under specific temperature and pressure conditions, and it tends to transform into amorphous ice over long periods at the extremely low temperatures of space. Yet here it is, suggesting that either 3I Atlas hasn't been as cold as we assumed, or something has been actively maintaining these crystal structures during its journey. This crystalline ice discovery has implications that ripple through multiple areas of planetary science. If the water ice in 3I Atlas has maintained its structure for billions of years, it might preserve chemical signatures from the object's formation environment with unprecedented fidelity. We could be looking at frozen samples of the disk of material that surrounded another star system during its planet-forming phase, a kind of cosmic archaeology that lets us examine the building blocks of worlds we'll never visit. The timing of these discoveries couldn't be more dramatic. As 3I Atlas approaches its solar close encounter, the increased heating should trigger changes in how materials sublimate from its surface. Astronomers are watching for any shifts in the composition or behaviour of the coma, hoping that thermal stress might crack open the object's surface and expose fresh materials that have been protected since its formation. But there's something else happening that's captured the attention of researchers worldwide, something that pushes beyond conventional cometary behaviour into territory that makes even seasoned astronomers pause and reconsider their assumptions. The object's approach trajectory continues to reveal statistical anomalies that seem to pile up like cosmic coincidences, each one individually explainable but collectively forming a pattern that challenges probability in ways that make scientists uncomfortable. Recent precision tracking has shown that 3I Atlas will pass within optimal observation range of Earth-based telescopes for an unusually extended period. Most interstellar objects zip through our solar system so quickly that detailed study becomes a race against time. But this ancient wanderer seems to have timed its visit to maximize our opportunity for investigation. It's almost as if the universe has conspired to give us the best possible view of something it particularly wants us to notice. The extended visibility window has allowed astronomers to detect subtle periodicities in the object's brightness that weren't apparent in earlier observations. These variations suggest a complex rotation pattern, possibly indicating that 3I Atlas isn't tumbling chaotically like most comets, but instead maintaining a more stable orientation as it travels. This kind of rotational stability is extremely unusual for natural objects, especially ones that have presumably been buffeted by stellar winds and gravitational perturbations during their billion-year journey through space. Temperature mapping of the object's surface has revealed another puzzle. Instead of the uniform heating pattern you'd expect from a simple comet nucleus, 3I Atlas shows distinct hot and cold regions that don't correlate with its orientation toward the Sun. Some areas remain stubbornly cool despite receiving direct solar radiation, while others seem to generate heat from internal sources. This thermal heterogeneity suggests a complex internal structure that goes far beyond what we'd expect from a simple chunk of ice and rock. The chemical analysis of materials streaming away from 3I Atlas has also yielded surprises. Along with the expected water vapor and dust particles, spectroscopic observations have detected trace amounts of rare isotopes that shouldn't exist in significant quantities in natural solar system materials. These isotopic signatures suggest formation conditions unlike anything in our cosmic neighborhood, possibly indicating origin in a stellar environment, with dramatically different nuclear processes than those that shaped our own planetary system. Perhaps most intriguingly, the ratios of these rare isotopes don't match any known stellar nucleosynthesis patterns. It's as if 3I Atlas formed in a type of star system that doesn't exist in our current understanding of stellar evolution, or perhaps during an era when the galaxy's chemical composition was fundamentally different from what we observe today. The implications for our understanding of cosmic chemical evolution could be profound. The international collaboration studying 3I Atlas has grown into one of the largest coordinated astronomical research efforts in history. Teams from over 30 countries are contributing observations, with data flowing in real time to analysis centres around the globe. The level of cooperation has been remarkable, with researchers sharing not just data, but also observational strategies and theoretical models in ways that transcend traditional institutional boundaries. This collaborative spirit has led to some unexpected discoveries. When researchers from different institutions began comparing their independent observations, they noticed discrepancies that initially seemed like measurement errors. But as more data accumulated, it became clear that 3I Atlas was actually behaving differently when observed by different instruments, almost as if it were responding to the specific wavelengths of light being used to study it. The phenomenon is subtle, but consistent. Radio observations detect activity patterns that don't correlate with optical measurements taken simultaneously. Infrared spectroscopy reveals molecular signatures that seem to fade when the object is simultaneously observed in visible light. It's as if 3I Atlas has some kind of sensitivity to being watched, though the physical mechanism that could explain such behavior remains completely mysterious. These observational inconsistencies have led to heated debates within the research community. Some scientists argue that the discrepancies result from instrumental calibration issues or atmospheric effects that haven't been properly accounted for. Others suggest that 3I Atlas might have surface properties that respond dynamically to different types of electromagnetic radiation, possibly indicating a composition unlike anything we've encountered before. The controversy has intensified as more research groups report similar findings. A team using the Very Large Telescope in Chile observed sudden changes in the object's spectroscopic signature that coincided precisely with the beginning of simultaneous observations by the Hubble Space Telescope. The probability of such timing being coincidental is vanishingly small, yet the alternative explanations venture into territory that challenges fundamental assumptions about how matter and energy interact. Ground-based amateur astronomers have also contributed to this growing body of anomalous observations. Their smaller telescopes and different observational techniques have detected variations in 3I Atlas's behavior that weren't apparent to larger, more sophisticated instruments. This democratization of discovery has created a situation where backyard observers are making contributions to cutting-edge research, their simpler instruments sometimes revealing phenomena that escape more complex detection systems. The role of citizen scientists in the 3I Atlas research effort has highlighted how astronomical discovery has evolved in the digital age. Online platforms allow amateur observers to share their data instantly with professional researchers, creating a global network of eyes on the sky that operates around the clock. This distributed observation system has captured variations in the object's behavior on timescales that would be impossible for any single observatory to monitor continuously. Social media has also played an unexpected role in the research effort. Observers around the world share real-time updates about 3I Atlas's appearance and behavior, creating a kind of crowdsourced monitoring system that complements formal scientific observations. While not all of these reports meet rigorous scientific standards, the sheer volume of observations has helped identify patterns and anomalies that might otherwise have been missed. The public engagement surrounding 3I Atlas has reached levels rarely seen for astronomical discoveries. News outlets struggle to explain the object's significance to general audiences, often resorting to dramatic comparisons and speculative scenarios that don't always align with scientific consensus. Yet this media attention has also generated unprecedented interest in astronomy and space science, inspiring a new generation of students to pursue careers in fields related to interstellar research. Educational institutions have embraced 3I Atlas as a teaching opportunity, using its story to illustrate concepts ranging from orbital mechanics to stellar evolution to the scientific method itself. Students around the world are learning about spectroscopy by analysing actual data from the object, getting hands-on experience with the same techniques used by professional astronomers. This educational impact may prove to be one of 3I Atlas's most lasting contributions to human knowledge. The technological advances driven by 3I Atlas research are already finding applications beyond astronomy. New image processing algorithms developed to analyze the object's subtle brightness variations are being adapted for medical imaging and materials science. Advanced spectroscopic techniques refined during the observation campaign are proving useful for environmental monitoring and industrial quality control. Private companies have begun investing in technologies specifically designed for interstellar object research, recognizing that future discoveries of this type could drive demand for specialized instruments and analysis capabilities. The commercial space industry sees potential opportunities in developing rapid response spacecraft that could be launched to intercept newly discovered interstellar visitors, though the technical challenges of such missions remain formidable. The economic impact of 3I Atlas research extends beyond direct technological applications. The international collaboration required for the observation campaign has strengthened scientific partnerships between institutions that may lead to future joint projects and shared funding initiatives. The diplomatic benefits of scientific cooperation often extend far beyond the immediate research goals, creating connections that can improve international relations in ways that purely political negotiations cannot achieve. As 3I Atlas continues its approach toward perihelion, the intensity of observations is reaching unprecedented levels. Major observatories are dedicating significant portions of their observing time to monitoring the object, sometimes at the expense of other important research projects. The scientific community has made a collective decision that this opportunity is too valuable to miss, even if it means delaying other discoveries. The pressure on individual researchers has become intense as the window for detailed observations gradually narrows. Career-making discoveries could emerge from the data being collected over the next few weeks, but the same observations could also reveal nothing more than an unusually large but otherwise conventional comet. The uncertainty creates a mixture of excitement and anxiety that permeates research institutions around the world. Graduate students and postdoctoral researchers find themselves at the center of one of the most significant astronomical investigations of the century. Many are working around the clock to process and analyze data as it streams in from observatories, knowing that their findings could influence the direction of interstellar research for decades to come. The responsibility is enormous, but so is the opportunity to contribute to humanity's understanding of its cosmic environment. The data storage and processing requirements for 3I Atlas research have pushed computational resources to their limits. Terabytes of spectroscopic data, imaging information, and measurement logs are being generated daily, requiring sophisticated analysis pipelines that can extract meaningful patterns from the flood of information. Artificial intelligence and machine learning algorithms are being deployed to identify subtle signals that might escape human analysis. cloud computing platforms have become essential infrastructure for the research effort, allowing teams around the world to share processing power and storage capacity. The distributed nature of the analysis work means that discoveries can emerge simultaneously from multiple research groups, creating both opportunities for collaboration and potential conflicts over publication priority. The sheer volume of data being collected about 3I Atlas will likely provide material for research papers and analysis for years to come. Even after the object has departed our solar system and faded from view, astronomers will continue mining the observational archives for subtle patterns and relationships that weren't apparent during the initial observation campaign. This extended analysis phase often yields some of the most important scientific insights, as researchers have time to examine the data from multiple perspectives and develop more sophisticated theoretical models. The legacy of 3I Atlas may ultimately extend far beyond what we learn about this particular object. The observation techniques, international collaboration models, and data analysis methods developed for this research effort are establishing new standards for how the astronomical community responds to rare and time-sensitive discoveries. Future interstellar visitors will benefit from the infrastructure and expertise developed during the 3I Atlas campaign. The psychological impact on the research community shouldn't be underestimated either. Many astronomers entered their field hoping to make discoveries that would fundamentally change our understanding of the universe. Atlas offers that possibility, but it also carries the weight of expectation and the fear of missing something crucial. The emotional investment in this research effort is as significant as the scientific and financial resources being devoted to it. As October approaches and 3I Atlas draws ever closer to its date with solar destiny, the astronomical world finds itself poised on the edge of what could be the most significant discovery in interstellar research. The ancient wanderer has already challenged our assumptions about cometary behavior, interstellar object populations, and the statistical likelihood of cosmic coincidences. But the story is far from over. The most intense observations lie ahead as 3I Atlas approaches its closest encounter with our Sun and potentially reveals secrets that have been locked away since the galaxy was young. What we discover in the coming weeks may reshape our understanding of planetary formation, stellar evolution, and the very nature of the materials that drift between the stars. The universe has delivered to our doorstep an artifact from its deep past, a messenger from distant worlds that carries within its ancient ice and rock the chemical signatures of stellar environments we can barely imagine. How we interpret the message it brings may determine not just our understanding of this particular object, but our entire conception of how matter and energy have evolved throughout cosmic history. And somewhere in the growing mountain of data, in the subtle patterns hidden within spectroscopic signatures and brightness variations, in the statistical anomalies that continue to multiply with each new observation, lies the answer to perhaps the most intriguing question of all. Exactly what kind of cosmic messenger has chosen to visit us during this brief moment in the vast expanse of space and time? The answer to that question may be emerging from an unexpected source. While professional astronomers focus their sophisticated instruments on tracking 3I Atlas's approach, a network of amateur radio operators around the globe has been quietly monitoring electromagnetic emissions from the object's vicinity. What they've discovered has sent ripples of excitement and concern through both the amateur radio community and professional research institutions. These radio enthusiasts, working with equipment that costs a fraction of what major observatories spend on single components, have detected structured patterns in the radio noise surrounding 3I Atlas. The signals are faint, barely distinguishable from cosmic background radiation, but they exhibit characteristics that natural phenomena rarely produce. Regular periodicities, frequency modulation, and what appears to be information encoding have all been documented by multiple independent observers. The discovery emerged almost by accident. Radio operators scanning for satellite communications and meteor reflections began noticing unusual signals that seemed to move across the sky in sync with 3I Atlas's predicted position. At first, most dismissed these detections as interference from terrestrial sources or equipment malfunctions. But as more operators reported similar findings, a pattern began to emerge that couldn't be easily explained away. Professional radio astronomers initially expressed skepticism about these amateur observations. The sensitivity required to detect such faint signals from an object millions of kilometers away should exceed the capabilities of backyard radio setups. Yet when major radio telescopes were directed toward 3I Atlas's position, they confirmed the presence of electromagnetic activity that hadn't been apparent in previous observations focused on other wavelengths. The signals don't match any known natural radio sources. Solar-wind interactions with cometary material typically produce broadband noise, not the narrowband emissions being detected. Plasma instabilities in the coma can generate radio waves, but not with the structured patterns that multiple observers are documenting. Each potential natural explanation seems to fall short of accounting for the full range of phenomena being observed. More puzzling still is the timing of these radio emissions. They don't correlate with 3I Atlas's solar heating cycles or its rotational period. Instead, they seem to follow patterns that relate to the object's position relative to major planets in our solar system. When 3I Atlas passes through the orbital plane of Jupiter, the signal strength increases. As it approaches the inner solar system where Earth and Mars orbit, new frequency components appear that weren't present in earlier observations. The electromagnetic signatures have also been detected by deep space communication networks normally used for contacting robotic spacecraft throughout the solar system. These highly sensitive receivers, designed to pick up faint signals from probes billions of kilometers away, have registered transmissions emanating from 3I Atlas's vicinity that share characteristics with artificial communication protocols. The signals exhibit error correction coding, data compression techniques, and modulation schemes that naturally occurring phenomena simply don't produce. Space agencies around the world have been quietly investigating these radio anomalies while publicly maintaining focus on conventional astronomical observations. The implications of structured electromagnetic emissions from an interstellar object are so significant that confirmation requires the highest levels of scientific rigor. False alarms in this area of research can damage careers and institutional reputations in ways that take decades to repair. The detection of apparently artificial signals from 3I Atlas has created an unusual situation where amateur researchers are making discoveries that professional institutions are reluctant to acknowledge publicly. The scientific establishment's caution is understandable given the extraordinary nature of the claims, but it's also creating tensions within the research community about how to handle potentially paradigm-shifting observations. Meanwhile, the object continues its relentless approach toward perihelion, and each passing day brings new observational opportunities and fresh mysteries. Ground-based telescopes are now detecting structural details in 3I Atlas's nucleus that suggest a level of organization unlike anything seen in natural comets. High-resolution imaging reveals geometric patterns and surface features that appear too regular to result from random accretion processes. The nucleus itself seems to consist of multiple components arranged in a configuration that maximizes structural stability while minimizing stress concentrations. This kind of engineering optimization is common in spacecraft design, but virtually unknown in natural objects formed through gravitational collapse and collision processes. The implications are staggering, yet the evidence continues to accumulate from multiple independent sources. Thermal imaging has revealed another anomaly that's causing quiet discussions in research circles worldwide. The object's surface temperature distribution doesn't match what you'd expect from passive solar heating. Instead, certain regions maintain elevated temperatures that suggest internal heat sources operating independently of solar radiation. These warm spots appear to be arranged in patterns that correlate with the geometric features visible in optical images. The heat signatures also vary in ways that suggest active thermal management, rather than simple radiative cooling. As different parts of the object face toward or away from the Sun, the temperature patterns shift in ways that maintain overall thermal equilibrium. It's as if 3I Atlas has some mechanism for redistributing heat to prevent dangerous temperature extremes that could damage its structure. This thermal regulation capability becomes even more remarkable when you consider the object's ancient age and the extreme environments it has presumably encountered during its billion-year journey through space. Natural objects exposed to such conditions should show signs of thermal stress, impact damage, and radiation weathering. Yet 3I Atlas appears to have maintained structural integrity that seems almost impossible for a passive collection of ice and rock. The spectroscopic analysis of materials in the object's coma has also yielded results that challenge conventional explanations. Along with the expected water vapor and dust particles, researchers are detecting complex organic molecules that shouldn't survive the harsh radiation environment of interstellar space. These compounds include amino acids, nucleotide bases, and other building blocks of life that require very specific conditions to form and maintain their structure. More intriguingly, the organic molecules show isotopic ratios that don't match any known stellar nucleosynthesis processes. They appear to have been synthesized under conditions that don't exist naturally in stellar environments, suggesting either unknown cosmic chemistry or artificial production methods. The implications for astrobiology and our understanding of how life's building blocks distribute throughout the galaxy could be revolutionary. The detection of these complex organics has prompted intense speculation about 3I Atlas's potential biological significance. Could this ancient wanderer be carrying samples of extraterrestrial life preserved in its frozen interior? The possibility seems remote, yet the chemical evidence continues to point toward biological processes that shouldn't exist in a sterile chunk of cosmic debris. Microbiological analysis of the organic compounds detected in 3I Atlas's coma has revealed molecular structures that bear striking similarities to terrestrial biochemistry. The amino acids exist in the same chirality or handedness that characterizes Earth-based life, despite the fact that non-biological synthesis typically produces equal mixtures of left and right-handed molecules. This homochirality is considered one of the key signatures of biological processes. The nucleotide bases detected in the coma include not just the standard components of DNA and RNA, but also exotic variants that don't exist in terrestrial biology. These modified bases could represent evolutionary adaptations to extreme environments, or entirely different approaches to genetic information storage. Either possibility would have profound implications for our understanding of how life might evolve under conditions radically different from those on Earth. Even more remarkably, some of the organic molecules appear to be organized into complex structures that resemble cellular components. Lipid-like compounds suggest the possibility of membrane formation, while protein fragments hint at sophisticated enzymatic processes. The preservation of such delicate structures over billions of years of interstellar travel seems virtually impossible, unless they've been actively maintained by some unknown mechanism. The biological implications of these discoveries have attracted the attention of astrobiological research institutes around the world. If 3I Atlas truly carries preserved samples of extraterrestrial life, it would represent the most significant discovery in the history of science. The possibility is so momentous that confirmation requires evidence that goes far beyond normal scientific standards. Contamination concerns have also complicated the analysis process. Any biological signatures detected in 3I Atlas's coma could potentially result from terrestrial contamination of the observational instruments or analysis procedures. Proving that complex organic molecules originated from the object itself rather than Earth-based sources requires extraordinary care in sample collection and handling. The international protocols for handling potentially extraterrestrial biological materials were developed primarily for samples returned from Mars or other solar system bodies. Atlas presents unique challenges because the material is being observed remotely rather than collected directly. Establishing the extraterrestrial origin of biological signatures requires inference chains that are vulnerable to contamination at multiple points. Space-based observations offer the best hope for avoiding terrestrial contamination, but they also provide limited opportunities for detailed analysis. The James Webb Space Telescope's upcoming observations of 3I Atlas will include searches for biological signatures, but the sensitivity limitations of remote sensing mean that definitive conclusions may remain elusive, even with the most sophisticated instruments available. The possibility that 3I Atlas carries biological materials has also raised questions about planetary protection protocols. If the object does harbour extraterrestrial life, even in preserved form, its passage through our solar system could potentially introduce alien organisms into our local environment. The probability of such contamination is extremely low, but the consequences could be catastrophic if it occurred. Biocontainment specialists have been quietly consulting with astronomical researchers about potential risks and mitigation strategies. The consensus is that the vast distances involved and the harsh conditions of space make biological contamination highly unlikely. But the unprecedented nature of the situation means that established protocols may not adequately address all possible scenarios. The debate over biological significance has also highlighted the challenges of distinguishing between natural and artificial origins for complex organic molecules. Some of the compounds detected in 3I Atlas's Comet could result from purely chemical processes operating under exotic conditions, while others might indicate biological activity or even technological synthesis. Drawing clear lines between these possibilities requires evidence that current observational capabilities may not be able to provide. As 3I Atlas continues its approach toward the inner solar system, the intensity of observations is reaching levels that strain the capacity of ground-based facilities. Every major telescope on Earth is dedicating time to monitoring the object, often at the expense of other important research projects. The scientific community has made a collective decision that this opportunity is too valuable to miss, regardless of the impact on other investigations. The coordination required for such an intensive observation campaign has created logistical challenges that extend far beyond normal astronomical operations. Scheduling conflicts between different research groups, data sharing protocols, and equipment maintenance requirements have all become matters of international concern. The window of opportunity for detailed observations is limited, and any technical failures or weather delays could mean the loss of irreplaceable scientific data. Weather monitoring at major observatories has become a matter of global scientific interest. Cloud cover that would normally cause minor delays in routine observations could now mean missing crucial data about one of the most significant objects ever studied. Backup plans involving multiple observatories and alternative observation strategies have been developed, but the finite nature of 3I Atlas's visibility window means that some opportunities, once lost, will never return. The psychological pressure on individual researchers has become intense as the stakes continue to rise. Graduate students find themselves operating million-dollar instruments while senior scientists coordinate international teams under unprecedented time pressure. The emotional investment in the research effort rivals the scientific and financial resources being devoted to it. Data processing centers around the world are operating at capacity as terabytes of observational information flow in daily from multiple sources. The volume of data being generated exceeds the storage and analysis capabilities of any single institution, requiring unprecedented levels of international cooperation and resource sharing. Cloud computing platforms have become essential infrastructure for managing the information deluge. Artificial intelligence systems are being deployed to identify patterns and anomalies in the data that might escape human analysis. Machine learning algorithms trained on decades of cometary observations are finding features in 3I Atlas's behavior that don't match any known natural phenomena. These automated analysis systems are generating alerts and flagging unusual signatures faster than human researchers can investigate them. The real-time nature of the observations means that discoveries are being made and shared almost instantaneously through online platforms and social media. The traditional scientific publishing process, with its months-long peer review cycles, cannot keep pace with the rapid flow of new information. Researchers are adapting by sharing preliminary findings through preprint servers and online conferences that allow immediate dissemination of results. This accelerated pace of discovery and publication has created both opportunities and challenges for the scientific community. Important findings can be shared and validated quickly, but the pressure to publish rapidly also increases the risk of errors and premature conclusions. The balance between speed and accuracy has become a constant source of tension among researchers working on 3I Atlas-related projects. Media coverage of the research effort has reached unprecedented levels for an astronomical discovery. News outlets struggle to convey the technical complexity of the observations while maintaining public interest in what might seem like an abstract scientific investigation. The challenge of explaining concepts like spectroscopic analysis and orbital mechanics to general audiences has led to simplified explanations that don't always capture the true significance of the findings. Public interest in 3I Atlas has also generated funding opportunities that wouldn't normally be available for pure research projects. Private foundations and government agencies are providing emergency funding for observation campaigns and data analysis efforts, recognizing that this may be a once-in-a-lifetime opportunity to study an interstellar visitor in detail. The educational impact of 3I Atlas research extends far beyond professional scientific institutions. Universities around the world are incorporating real-time observations of the object into their astronomy courses, giving students hands-on experience with cutting-edge research techniques. High schools and middle schools are using simplified versions of the data analysis tools to introduce younger students to scientific methods and space science concepts. Amateur astronomy clubs have organized observation campaigns that complement professional research efforts. While their equipment may not match the sensitivity of major observatories, the distributed nature of amateur observations provides continuous monitoring capabilities that no single professional facility could maintain. This citizen science contribution has become an integral part of the overall research effort. The technological advances driven by 3I Atlas research are already finding applications in other fields. New image processing algorithms developed to analyze subtle brightness variations are being adapted for medical imaging and materials science applications. Advanced spectroscopic techniques refined during the observation campaign are proving useful for environmental monitoring and industrial quality control procedures. Private companies have begun investing in technologies specifically designed for interstellar object research, recognizing that future discoveries could create markets for specialized instruments and analysis services. The commercial space industry sees potential opportunities in developing rapid response spacecraft that could be launched to intercept newly discovered interstellar visitors, though the technical challenges remain formidable. The international cooperation required for 3I Atlas observations has strengthened scientific partnerships between institutions that may lead to future collaborative projects. These relationships often extend beyond immediate research goals, creating diplomatic connections that can improve international relations in ways that purely political negotiations cannot achieve. As October approaches and 3I Atlas draws closer to its solar encounter, the astronomical community finds itself confronting possibilities that would have seemed like science fiction just months ago. An ancient interstellar wanderer displaying technological signatures, biological materials, and behavioral patterns that challenge our understanding of what's possible in the cosmic environment between stars. The convergence of evidence from multiple independent sources has created a situation where even the most conservative researchers are beginning to acknowledge that 3I Atlas may represent something unprecedented in human experience. Whether that something is an exotic natural phenomenon operating under conditions we've never encountered or something else entirely remains to be determined. But one thing has become increasingly clear as the data accumulates and the anomalies multiply. 3I Atlas is not behaving like any cosmic object we've studied before. Its thermal regulation, electromagnetic emissions, structural organization, and chemical composition all suggest levels of complexity that natural processes rarely achieve. The statistical probability that all these unusual characteristics could occur together in a single object by pure chance has fallen to levels that make coincidence an increasingly unsatisfying explanation. The scientific community now faces a challenge that extends far beyond normal research protocols. How do you investigate a phenomenon that might require expanding our understanding of what's possible in the universe? How do you maintain scientific rigor while remaining open to possibilities that traditional theories cannot accommodate? These questions become more pressing with each passing day as 3I Atlas continues its approach toward the inner solar system. The ancient wanderer has already forced us to reconsider our assumptions about interstellar objects, planetary formation, and the distribution of complex materials throughout the galaxy. What it might reveal during its closest encounter with our Sun could reshape our understanding of our cosmic environment in ways we're only beginning to imagine. The universe has delivered to our doorstep something that defies easy categorization, something that carries within its ancient structure secrets that have been preserved for longer than our solar system has existed. Whether those secrets reveal new physics, exotic chemistry, preserved biology, or something else entirely, the answer lies just weeks away as this mysterious visitor prepares for its moment in the solar spotlight. And in that approaching moment of revelation, humanity stands ready to learn whether we truly understand the cosmos we inhabit, or whether 3I Atlas has come to teach us that the universe still holds surprises that could change everything we thought we knew about our place in the vast expanse of space and time.